There's the river right at the bottom. So don't expect these slides to be good because I think they were made again during, I made them in real time while we were Zooming, right? So you can see there's just a hit and miss of things. What do we got on our? One thing that was very short. It's a 1 page. All right, so it was even worse than I thought. The problem with this thing, closing this thing, is every time you hit the escape in order to get out of PowerPoint, it brings you down again. All right, but I think this is I think it's a good problem anyway. So the problem is as follows. And it's written up, the solution is written up in the practice test. Right, so we have a river and we have stones in one line. And you personally are standing here and you want to get to the other side, right? And the stones have some distance apart. And you are able to walk 1 meter. You can step 1 meter, right? And so clearly, if there are 2 stones that were more than 1 meter apart, you can't do it, right? But if that's not the case, then you could step on every stone and get across, right? But as you can imagine, our goal is to step on as few stones as possible. Right? And I bet you every kid who's ever crossed the river has thought about this game, right? So as a greedy algorithm, right, the stones are objects in our input, and the solution is you decide for every stone whether to take it or not. And the value of the solution is how many stones you take, and we want to minimize that, right? And it's valid. When is the solution valid is if you look at the stones that we've taken, you never step more than 1 meter, right? That's the definition of valid or conflict, right? Everybody good with that? So what is the obvious algorithm? The what? So you're standing here, and let's say that this is 1 meter, right?
It would be like 6,000 every 1 year. So they're like break down like compared to
Yeah, we're going to go as far as you can without getting wet, right? So then we're standing here, right? And from here you say, hey, we can step to there. So you go as far as you can without getting wet. Now we're stepping here. You go as far as you can without getting wet. Right? Does that make sense? That's the algorithm. Right? Right? So now we haven't talked about this yet. We've already talked about a non-adaptive greedy algorithms in which every object in your input is given a priority at the beginning and you sort them, right? A greedy algorithm, not greedy algorithm, an adaptive greedy algorithm adapts the priorities as you go, right? So for example, when I'm here, the priority of this stone is like, no, it's just infinite. Don't go there, right? Right? And so we would say the priority of a stone actually is how far it is. And then we'll give priority 0 to these, right? Or negative infinity to these. And so you take the one who goes the furthest that you can reach, right? And then when you move, the priorities of these change, right? Because suddenly you can reach them. So that's why it's an adaptive greedy algorithm. but it's not a big difference. Everybody kind of follow that? So what we have to do is, if we can just focus on the game, right? Let's just remember the game. So if you look up here, the first thing in the game is that the player tells you what he's done so far, right? He gives you AT minus 1. So there's AT minus 1 up there, where the green ones are clearly the ones that he's taking, right? And so he's standing on the rightmost green one. And then you can see AT is he takes the next green one, which is a little darker, right? And then remember the fairy godmother, she gives you an optimal, ideally an optimal solution, but certainly a valid solution, consistent with what the algorithm has done. All right. So here she has to be consistent with AT minus 1, right? So she has to take this one, she has to take this one, and she can take whatever else she wants. It's not none of her business, right? And then in our game, our job is to produce ST. And what does ST properties have to have, right? It has to be valid. And what does valid mean? You never set more than 1 meter. It has to be consistent with what the algorithm has done, right? So it needs this guy, and this guy, right? And it needs to be at least as good as what the fairy godmother has, right? And good means the number of stones, right? So the number of stones, it's okay for it to go down, but it can't go up, right? Does that make sense? And so we have to, the prover has to kind of come up with an algorithm or instructions on how to change ST minus 1 to be ST, right? So what's the change? Well, remember that I had that picture, which was, here's the road, the loop invariant road, and we first take a step, which is you gotta make things right for the algorithm, right? So the first step we're saying is, fairy godmother, you have to take this dark green one, right? That's our first change, right? And so that's reasonable. But if we just do that, what's the problem? Is it still valid? What? It's worse, right? The value is worse. We have one more stone to step on, right? And so it's worse. So we have to get her to delete at least one stone, right? At least one stone, right? Does that make sense? So which stones of hers do we get her to delete? These ones? Yeah, right? Everybody in the algorithm is stepping from here to here. So we say, fairy godmother, if you have any stones between here and here, delete them, right? And you see why I have a bunch of them here, just to show that she might be deleting a bunch of them, right? Does that make sense? Yeah, well, one of the changes I made this term was not to force the fairy godmother giving you an optimal solution. And the reason I did that was because we do have to consider all cases, right? And one of the cases is that she's giving you something bad, right? And in that case, you can say how to fix it, Or you could say, hey, that's impossible because it's bad. Either way, you have to consider the case. And I just got tired of that conversation. And so that's why I switched it to she's not committing to it being optimal, and we just have to make it at least as good as hers. Right? Does that make sense? Yeah, soon as if we can achieve something valid and delete more than one rock, then she was clearly not optimal. And my point is, let's not be mean to her, right? That's my only point. Let's consider that case and not. All right, so that's our instruction. Delete everybody in the middle, right? So now we've described a paragraph which says, how do we change ST minus 1 to ST, right? Now we need a new paragraph that proves that it's consistent with the algorithm. Was it consistent with the algorithm? Right? We brought that in, and the things that we're deleting are things in between the greens, right? So we're good with the algorithm, right? Is it valid? Are all the steps less than 1? Right? Yeah, so here, let's talk about the past. The algorithm's good at, we know we can get to this green one. Why? Because the algorithm did, right? And now, well, how do we know we can get from here to here? Right? Because the algorithm's, the fairy godmother's taking this one, right? So we have to be worried about how we can get from here to here. Yeah. Yeah. Alrighty. Right. So that's one problem. And once we're to here, right, we're good because we're following the algorithm, the prover, and that the fairy godmother. We're following the fairy godmother, right? So we had two issues. Is one, how do we get from here to here? And two, is it at least as good, right? I mean, we have to make sure that we're deleting at least one stone. Does that make sense? All right, so anybody want to venture? Let's prove that you're deleting at least one stone. How do you prove that? Yeah, let's do a proof by picture here for a minute. I'm going to delete those. Suppose there were none in there, right? Does it look like a good picture? What's the problem with the picture? Yeah, how does she get from here to here? Right? How do we know that that's not valid? The biggest, exactly. Both the fairy godmother and the algorithm are standing on this rock. The algorithm took the furthest one, right? That's reachable. So she might have taken the same one, in which case we don't have anything to do, right? If she took an earlier one, then we got what we had. We deleted somebody, right? But if she took a further one, then she's wet, right? Does that make sense? All right, so that confirms there's somebody in here, right? So that she can jump along, right? All right, so now let's figure out, how do we know that we can step from here to here? right?
The original one, at the -1, or we can, sorry, that mother can jump from the original one to the next one. It has to be within 1 meter.
Right.
So we are moving per step forward. That means, our distance with her next step will be, less than hers.
Brilliant, brilliant. That was a perfect answer, right? You look at the last one of hers that we delete. Say, let's say it's this guy here. Right? I can't grab him, but you imagine the last one that this one here, the last one, right? How does she get from here to here? Right? She has to do that. And so that step has to be at most a meter. And then look at from the dark green, we're concerned about the dark green to here, and it's a smaller distance. Right? Does that make sense? And that's the entire proof. Right? That's the entire proof. These arrows here, you know, I don't know what those, I think I mean, I drew them in as we were talking. I think this distance is the distance that the fairy godmother had to step, right? And she's able to do that. That's a distance almost a meter. And then this is the distance that we have to step now, right? And this distance is less than this distance. Yeah, I didn't even notice those meters, but those are exactly what we were just talking about, right? Does that make sense? And then I guess I put this one in because we don't have to worry about those because she's doing it, right? We don't have to worry about these because the algorithm's doing it, right? Does that make sense?